So, favourite scenario for a projectiles question, throwing objects from the top of a cliff. So let's see how we get on here with a little problem by the seaside. So here's the question, and the first thing I'm going to do is just draw a little diagram of what's going on. So there's our cliff, and the origin is the start of the motion, as is usually the case with SUVAT, and the angle alpha here, the angle with the horizontal initial speed of 17 meters per second, and the height of the cliff 30. So to try to find the greatest height above sea level reached by the stone, I need to look at the vertical direction. So I'm going to take the upward direction as positive, and we're using SUVAT. So I'm calling the displacement, I'm looking at the highest points here. So I'm looking at the motion from the origin to this point, and the displacement from the origin is going to be that number there, whatever that distance there is. I'm calling that S. The initial velocity is 17 sine alpha. The final velocity at that highest point is 0. The acceleration due to gravity. Gravity is in that direction, always pointing towards the center of the Earth, so the acceleration due to gravity is negative 9.8. And we're not interested in the time to get to that highest point just yet. So that's why I put not applicable here. What about sine alpha then? Before we actually write down the equation, sine alpha, we know that tan alpha is 28 over 45. So 28 over 45 is tan alpha. So using Pythagoras, we can work out the length of that side. So that's the easiest way to work out the missing side, and then sine alpha is opposite over hypotenuse, and cos alpha will be adjacent over hypotenuse. So that's how we do that. So the formula that doesn't include time, the SUVAT formula without time, is this one, v squared equals u squared plus 2as. Putting these values here into the formula gives us the equation there, and that is sine alpha there, 28 over 53. And when we click our calculator, we get S of 4.12. But remember, that is just the distance from the top of the cliff. The question asks us for the greatest height above sea level. So we need to add 30 to that. The greatest height above sea level is 34.12 meters. So that's part A complete. Let's look at the total flight time now. So the total flight time, what I'm doing is I'm looking at this, the whole of the flight now, and I'm looking at the time t there when the displacement, the vertical displacement, is minus 30. So I'm taking the positive direction being the upward direction once again, and the displacement, the time at which I'm interested in, time t, where the displacement is minus 30. The initial velocity is 17 sine alpha again, and I'm not interested in the final velocity at this stage. So the formula I want is the one that hasn't got v in it, and that's S equals ut plus half at squared. Popping those numbers into that formula gives me that, and then from there I get two values for t, and of course we're only interested in the positive one, so the total flight time is 3.56 seconds. So that's part B complete. So for part C now, the angle at which the stone enters the sea. So at the point where it enters the sea, its velocity will have a horizontal component and also a vertical component. So what I'm going to do is work out those two components first, and then we'll join them together to find the angle in a moment. So vertically, we're wanting to find the vertical component of velocity, which I'm calling Vy, at the time that we know that the stone hits the sea, 3.555 seconds. I'm being a little bit more accurate here just to make sure that I don't induce any rounding errors in my calculations. So this is the unrounded version of, or slightly less rounded version of the time that we calculated in part B. The acceleration is minus 9.8 and the initial velocity is 17 sine alpha again. So we want the formula that doesn't have s in it. So v squared equals, v equals u plus at. And from that we get a vertical component of velocity of minus 25.91. So we've got in that direction 25.91 meters per second. What's the horizontal component of velocity? Well, horizontally the acceleration is 0, so that means that the horizontal component of velocity will be constant, and that is 17 cos alpha. So the horizontal component of velocity is 14.43. So we've got a figure of 25.91 going in that direction, 14.43 going in that direction. So our velocity of the stone as it hits the sea is in that direction there. We're looking for this angle here. So this is simple trigonometry now. Tan theta is opposite over adjacent. So theta is tan to the minus 1 of that, which is 61 degrees. So there we are, that's that question.